Welcome back to the deep dive. If you're wrestling with general relativity, cosmology, maybe even the weirdness of thermodynamics, these fields really push right up against the edges of what we understand. Today, we're diving into one of those edges specifically, the work on black holes, singularities, and the geometry of space-time that won Roger Penrose his share of the 2020 Nobel Prize. We're basing this deep dive on excerpts from Penrose's own Nobel lecture, so we get to follow his thinking, see the tools he used, and explore some pretty radical ideas that came out of it all. Okay, setting the scene. General relativity, Einstein's theory, it predicted black holes, these totally bizarre zones where gravity is so strong light itself can't get out. But for a long time, many top physicists, Einstein included, were pretty skeptical. The math worked for, perfect scenarios, like a perfectly round star collapsing. But the actual universe, messy, asymmetrical, could these things really form?
That's exactly right. The big hang-up was the singularity, that point of infinite density, infinite curvature, predicted right at the center in simple models like the Oppenheimer-Snyder collapse. The worry was, well, you'd only get that singularity if the collapse was perfectly, almost unphysically symmetrical. Any real-world imperfection, a bit of rotation, a lump. They figured that would mess things up and prevent the singularity, and maybe the whole black hole picture as we understood it.
Right. And this is exactly where Roger Penrose just completely changed the game. He came in with these really original mathematical tools and basically proved that no, black hole formation, singularity included, is a robust prediction of general relativity. It doesn't need that perfect symmetry. It's generic. It happens even with messy, uneven collapsing stars. His work was the solid theoretical bedrock showing black holes belong in Einstein's universe. And of course, the other half of that Nobel went to Reinhard Genzel and Andrea Ghez for finding that, well, that stunning observational proof, the supermassive invisible object, 4 million solar masses, right at the heart of our Milky Way.
Absolutely. And Penrose brings such a unique viewpoint. I mean, he's not just the singularity theorems guy. Penrose tilings, Penrose diagrams for visualizing spacetime, they're essential tools now. It shows this amazing blend he has of deep mathematical rigor and real physical intuition, crucial for these kinds of problems. Plus, he's pretty good at explaining things, which helps us here.
Okay, let's get into how he did it then. Penrose's approach was about looking at general relativity differently. It starts, fundamentally, with Minkowski's 1908 idea of 4D spacetime. Space and time woven together, that's the stage for GR.
Right. So picture this 4D spacetime. At every single point, you've got what's called a null cone or light cone. It basically maps out all the possible paths light rays can take from that point. The local speed limit, geometrically. Now, in general relativity, gravity isn't a force in the old sense. It's the curvature of this space-time. And that curvature can tilt and distort these light cones. This tilting means light rays can get focused. They can cross over each other, creating caustics. Think of light focusing through a lens or shimmering off water. Penrose saw that understanding the geometry of these cones, how light behaves, was key. More key, maybe, than just tracking the matter itself.
Okay, and here's where it gets really interesting and maybe a bit unexpected if you're mostly used to thinking about GR with tensors. Penrose leaned heavily on two spinors. Where did that come from?
Yes, fascinating. It came from quantum mechanics, actually, from Paul Dirac's work on the electron, which uses four spinors. Penrose learned about them, apparently from Dirac himself, and realized they offered this powerful, kind of underused perspective on general relativity structure.
So what do these two spinors let you do that's so useful for GR?
Well, they provide a very elegant way to break down or decompose space-time curvature. Curvature in GR, you can think of it splitting into two bits. There's the Ricci curvature. That's the part directly linked to matter and energy, the density, the pressure, the stuff on the right-hand side of Einstein's equations. But then there's the Weyl curvature. That's the rest of it. It describes the free gravitational field, the part that can exist even in empty space. Think gravitational waves. It's the Weyl curvature that causes tidal forces that's stretching and squeezing. Or, as Penrose described it, is what would distort your view of the constellations if a gravitational wave passed by. And Penrose found that the equations for this Weyl curvature look particularly neat, particularly insightful, when written using two spinors. It gave him a different geometric handle on how space-time could warp and twist independent of the matter right there.
Okay, so he's got this deeper geometric insight, especially about light paths and weak curvature. How did he apply that back to the big question? Do singularities really happen in realistic collapses? He knew about the simple Oppenheimer-Snyder model, the perfect dust cloud collapsing to a point.
Right, and people also knew the Schwarzschild solution, the vacuum outside a spherical mass. There's that coordinate issue, the Schwarzschild singularity at the event horizon radius. But Finkelstein had shown that was just, well, a bad choice of coordinates. The real physical singularity in that solution was still at the center, R0. Penrose really got Finkelstein's point. The singularity wasn't some boundary effect, it was tied to the deep interior. But again, could it happen without that perfect spherical symmetry? The common wisdom back then, maybe influenced by some Soviet work by Lifshitz and Kalatnikov, seemed to suggest maybe not, that singularities were special, not general.
And then came Penrose's killer idea, the concept that just cracked it open, the trapped surface. Can you walk us through that?
It is weird. Okay, imagine a closed surface in space, like a sphere. Normally, if you flash lights outwards from every point on the sphere, the light rays would spread out, right? Diverge. A trapped surface is a surface where space-time is so warped by gravity that if you flash lights outwards, the light rays actually converge inwards. They move towards each other. And here's the kicker. Even if you flash the lights inwards, they still converge inwards. Both outgoing and ingoing light rays originating from the surface are forced to converge. It's like a boundary of no escape, defined purely by the local geometry, how the light cones are tilted. It doesn't need to be a physical boundary or anything.
Wow, okay, so this geometric thing, this trapped surface, what does its existence imply for the collapse?
That was the absolute key. Penrose proved a theorem in his famous 1965 paper. He showed that if you have normal matter satisfying what's called an energy condition, basically saying energy density isn't negative, which is very reasonable, and if gravitational collapse proceeds far enough to form one of these trapped surfaces, then inevitably space-time must contain a singularity in the future. The paths of things, like light rays or particles, just can't be continued. They hit a wall. His theorem showed that once a trapped surface forms, a singularity is guaranteed. It doesn't matter if the collapse is lopsided, rotating, messy.
Right.
If you trap light like that, you get a singularity.
So that was it. That was the proof that singularities aren't just artifacts of perfect math problems.
Exactly. It showed there are robust, generic consequences of general relativity when gravity gets strong enough. That fundamentally shifted everything. Black holes went from being mathematical curiosities to unavoidable predictions.
Incredible. And that work didn't just stay with black holes, right?
No, not at all. The mathematical techniques Penrose developed for proving singularity theorems were extremely powerful. Stephen Hawking saw that immediately. Hawking adapted and extended these methods, and together they applied them to the whole universe. Their joint work, the Penrose-Hawking singularity theorems, showed that under very general conditions, basically that the universe is expanding and gravity is attractive, our universe must have started from a singularity in the past, the Big Bang singularity. So Penrose's ideas were fundamental not just for the end state of stars, but for the beginning of everything.
But that brought up a puzzle Penrose himself points out. If his theorem suggests singularities should generally be complex, messy things, why does the one singularity everyone talks about, the Big Bang, seem so incredibly smooth and simple? He mentions asking the cosmologist Jim Peoples about this, and Peoples apparently just said, because the universe is not like that, which is blunt.
It is blunt, but it highlights a massive discrepancy. We look at the cosmic microwave background, the CMB, the heat left over from the Big Bang. It's unbelievably uniform across the sky. Smooth, ordered. That suggests the very early universe was in this incredibly special low entropy state. But Penrose's own theorems imply gravitational collapse should generally lead to chaotic, high-entropy singularities. Now, the standard explanation for the smoothness is inflation, a hypothetical period of hyperfast expansion right at the beginning. But Penrose felt this smoothness pointed to something deeper, a fundamental difference between the type of singularity in our past, the Big Bang, and the type found in our future, inside black holes. A puzzle about time zero, really.
And you can connect this to the second law of thermodynamics, too, right? The idea that entropy disorder always increases.
Exactly. Think about perfume in a bottle that's ordered, low entropy. Open it, it spreads out, fills the room disordered, high entropy. The second law says things tend to go from ordered to disordered. A smooth, uniform CMB looks, in terms of matter distribution, like a high thermal entropy state, like the evenly spread perfume. But wait. Gravity does the opposite. Gravity pulls things together. It takes a smooth distribution of gas and dust and makes it clump into stars, galaxies, eventually black holes. That looks like structure formation, like decreasing randomness, at least locally.
So where does the increasing entropy go?
Well, Bekenstein and Hawking showed black holes themselves have enormous entropy, huge amounts. The entropy is proportional to the area of their event horizon. So the picture becomes the universe starts smooth and low entropy, at least gravitationally speaking, and evolves according to the second law, with most of the entropy eventually ending up locked inside black holes. Penrose connects this to the Weyl curvature again. He
Mm-hmm.
argues that the Big Bang singularity must have had effectively zero Weyl curvature, making it very smooth, gravitationally low entropy. But the singularities inside black holes, they can have potentially infinite Weyl curvature, maximum gravitational entropy. So there's this profound asymmetry. The past singularity was simple, future singularities are complex. Why? That's the deep puzzle.
And trying to resolve this puzzle, this asymmetry, led Penrose down a really mind-bending path. Conformal Cyclic Cosmology, CCC, starts thinking about infinity using conformal geometry. What's that about?
Right. Conformal geometry is a way of transforming space where you preserve angles, but you can stretch or shrink distances. Think of those M.C. Escher prints where figures get smaller and smaller towards the edge, but keep the same shape locally. That's often a conformal mapping of an infinite space onto a finite disk.
Okay, how does that help with cosmology?
It's relevant because light rays, the null cones we talked about,
Yeah.
define the causal structure of space-time, what can affect what, and the physics of massless particles, like photons, is conformally invariant. Their physics doesn't care about the overall scale factor of the universe, only the angles, the cone structure. Penrose had this idea. What if you use conformal geometry to view the whole history of the universe? You could mathematically squash the infinitely distant future, which is expected to become cold, empty, dominated by massless photons as matter decays or flies apart. You could squash that infinite future down to become a finite boundary. And kind of symmetrically, you could stretch out the initial Big Bang singularity, which was infinitely dense and hot, into another finite boundary.
And this leads to the crazy idea. CCC. What if that conformally squashed future boundary of our universe could somehow become the conformally stretched Big Bang boundary of the next universe?
Exactly. A cycle. Our universe's far future smoothly transitions via this conformal rescaling into the Big Bang of a subsequent eon. And our Big Bang, that was the conformally mapped far future of a previous eon.
Okay, wait. For that to work, don't you need everything to become massless in the far future? What happens to protons, electrons?
That's a huge requirement. The idea assumes that over truly immense timescales, perhaps via mechanisms we don't fully understand yet, all massive particles effectively decay or lose their mass, so the very far future is dominated only by conformally invariant stuff like photons and maybe gravitons. It's a big assumption.
What's the physical appeal, though? Why
Yeah.
propose such a cycle?
The appeal is trying to solve that entropy puzzle. In CCC, the low-entropy smooth state of our Big Bang isn't some arbitrary initial condition. It's inherited from the conformally squashed, spread-out, high-entropy, but gravitationally simple, low-Weyl curvature state of the previous eon's far future. The physics near the Big Bang, very hot, very dense, high kinetic energy making rest mass less relevant, might look mathematically similar after conformal scaling to the physics of the very cold, very diffuse, massless far future.
Okay, my head hurts a bit, but this is physics, so
Wow.
are there predictions? Can we test this wild cyclical idea?
Penrose argues yes. He suggests looking for specific imprints in our CMB, signals that could have leaked through, so to speak, from the previous eon into ours. He focuses on two main types. First, rings of low temperature variance in the CMB map. The idea is that supermassive black hole mergers in the previous eon would have created enormous ripples in space-time gravitational waves. These waves, Penrose suggests, could pass through the conformal boundary into our eon, leaving faint, concentric, ring-like patterns where the temperature fluctuations in the CMB are slightly suppressed. He and collaborator Vahe Ghazadian analyzed Planck satellite data and claimed to find evidence for such concentric rings, even suggesting the centers of these ring patterns imply a clustered distribution of ancient black holes, very different from standard cosmology. It's controversial, but it's a prediction.
Okay, rings from past black hole collisions. What's the second type of signal?
Hawking points. This relates to Hawking radiation, the idea that black holes aren't totally black, but slowly evaporate over vast timescales. Penrose considers supermassive black holes from the previous eon that survived almost until the end, finally evaporating right around the crossover time into our eon. All the energy from that final evaporation, he argues, would effectively pass through the conformal boundary as a concentrated burst. As this energy propagates into our eon, it spreads out. By the time the CMB forms, this energy would appear as a small, unusually hot spot on the CMB sky, a Hawking point.
And does he look for those?
Yes. In work with various collaborators, they predicted these points should be significantly hotter than typical CMB fluctuations, maybe 15 times the standard deviation. And Penrose claims they do find these anomalous hotspots in both the WMAP and Planck datasets, sometimes with extremely high statistical confidence, like 99.98% for certain points found in the Planck data. He stresses that some key candidates appear in the same locations in both independent datasets. He argues quite strongly that these points are real features demanding explanation, whether by CCC or some other theory beyond standard inflation.
Wow. Okay, so from proving singularities are basically unavoidable in GR, something people really doubted, to using that deep understanding to propose this grand cosmic cycle theory and pointing to potential, albeit debated, fingerprints in the CMB. Penrose's work, it's just this incredible arc rooted in deep math, deep geometric thinking about GR, challenging our picture of black holes, the Big Bang, maybe the whole story of reality.
Absolutely.
Yeah.
His way of using tools like two-spinners, focusing on the Weyl curvature, inventing the concept of trapped surfaces, these were the breakthroughs needed to show black holes were real predictions of Einstein's theory. And then applying those same rigorous methods with Hawking to cosmology revealed that profound puzzle about the Big Bang's smoothness and the arrow of entropy.
And CCC, well, it's definitely out there, highly speculative, and the evidence is still very much under scrutiny in the community. But it's a fascinating attempt to resolve those deep puzzles, and it makes these really specific, potentially testable predictions.
Yeah.
You have to admire the boldness.
It really underscores how looking at the fundamental geometry, looking at space-time structure in new ways, can lead to completely unexpected insights about the universe's extremes and its origins.
So, thinking about you listening, maybe you're a physics student just getting into GR, cosmology, quantum field theory. Penrose's journey is pretty inspiring, isn't it? It shows how diving deep into the theory, asking fundamental questions, and maybe even picking up less common mathematical tools like two-spinners or conformal geometry can genuinely shift our understanding. The biggest puzzles aren't solved yet.
Which leaves us with a pretty big thought to chew on. If something like CCC is even remotely on the right track, if there are signals crossing over from a previous cosmic eon, what does that tell us about which physical laws might persist across these boundaries? Could we actually learn something concrete about physics before our Big Bang by studying these potential relics? What would that even mean?
Definitely something to think about. Keep asking those big questions. Thanks for joining us for this deep dive.